Let's talk about an example Turing machine. This Turing machine accepts all strings with the string 101 in between. So if you look at this Turing machine, on the first state A, if we encounter a 0, then we write down a 0 and the head moves to the right. If you encounter a 1, then you write down a 1 and the head moves to the right, but the state is also changed. Then if you are in the B state, with the 0, you write down 0, move right, and also change the state to C. But if you encounter a 1, then you stay there in the sense of the state, but the head does move to the right. So this is the difference. So you're not just talking about moving the state, you're also talking about moving the heads. So one can define a Turing machine formally as a 7-tuple. So what does that mean? It means it will have different sets. The first is a set of states, which is Q. Now, we would be incomplete if we do not have an input alphabet. So sigma represents the input alphabet. Gamma is the tape alphabet. Now Q naught is the start state. HA is the unique acceptance and halting state. HR is a unique halt and reject state. Now this is rarely drawn. Delta is the transition function. So it is the cross product of Q and gamma and results in Q and gamma and either move to the left or right or stay. In this next example, we see a Turing machine 0n, 1n. For this Turing machine, it must accept all strings which have a similar form. So all the zeros and ones must be paired off. So what we do is we repeatedly erase first the 0 and the last one until epsilon is reached. In pseudocode, this would be written as if head symbol equals 0, then write delta, else reject. Move head to the right until the head symbol equals delta. Move head to the left. If head symbol equal 1, then write delta, else reject. Move head to the left until head symbol equal delta. Move head to the right. And finally, if head symbol equal delta, then accept. And then you go back to 1. So if you look at this diagram, you see we start with the state A. In case of a 0, we replace it with delta and move the head to the right. We also move from the A state to the B state. Now, likewise, if we're in the B state, we can encounter a 0 or a 1 or a delta. If it's a 0 or 1, the head will move right, but if you get delta, then you move to the left, and so on. So we can look at an execution of this Turing machine on the string 00111. So first what happens is we start with the state A and the head is pointing on 0. Now we move to the state B. 0 has been replaced by delta, and this keeps going till we get to the point in the next position where it's the state is C, we're pointing to 1. So we write down our delta and then so on. Finally, we realize that we've written a lot of deltas, but we're still left with 1, which means it is a reject. Now, there are Turing machines which simply do not halt. Here's an example of a Turing machine. You see, there's no except state here. So, what happens is it keeps moving back and forth between the two states on and on. So, it's obvious from this diagram that there is no except state, so it will never halt, either for accept or for reject. Another example Turing machine is for balance brackets. What are balance brackets? Oftentimes in programs, we need to find the balance brackets. So you have to match the innermost matching pair of brackets, erase them, and then keep going. So for this process, we have to use a special symbol to indicate an erase bracket. In this case, the example given here is of x. So whenever we want to erase a bracket, we write down x. So if you see here, it looks a little bit weird, but it's still a Turing machine and it's written in the same notation. So if you encounter the left bracket, you write it down again and move to the right. If you encounter is x, then you let it be there and then move to the right, and the state in both cases remains the same. And likewise, this keeps going. Another example is that of palindromes. In palindromes, if it's even length, so we first match the two symbols on the side, so the first and the last symbol, and erase them. Then keep repeating. If we reach epsilon without mismatch, it means the string is a palindrome. So in case can be solved. So let's look at an example Turing machine. Here we see the different states A, B naught, C naught, B1, C1, and D. The way this machine works is you start out with the state A. If you encounter a 0, then you write down delta and move to the right. If you encounter a 1, you write down delta and move to the right. And if you encounter delta, then you also write delta and stay, and then you move to the accept state. As you can see here in this machine also, not only does the head move to the right, left, or stay, the machine also moves from the states. Now, we do not represent a Turing machine always using diagrams. An easy way to represent a Turing machine is to write down its pseudocode, which is plain English. So let's look at an example Turing machine, a machine that recognizes a common problem, a language W hash W. So there are two words and they are the same, and they are separated by a symbol hash. So if we look here, how this works is it essentially moves so that it finds the first entry, crosses it off, and remembers. Then it starts moving to the right until the first entry is found again after the selected symbol, which is the hash mark. If it is correct, it crosses that off, returns back to the leftmost uncrossed entry, and the process repeats itself. It ignores the crossed out symbol. So this Turing machine, it will accept if it is able to cross out all the symbols without encountering any problem. Now, if you look closely at a Turing machine, it does look like a small computer, maybe with a limited instruction set. However, we can see that it can certainly perform complex tasks. Now, if one aid to that is to design a Turing machine subroutine. So, what that means is that we have some basic tasks that are very useful and we design them, the Turing machines for these tasks. That would really help us. Let's take an example subroutine. Now, this subroutine shifts the input time entirely, one cell to the right. So, we can make an inefficient one or we can make an efficient one. If it were an inefficient one, it would move the rightmost symbol over then the next one and so on. That is, every time it has to move to the end of the string. Remembering the last string, the last symbol as it goes, and then when it reaches the right hand, it writes down the remembered symbol. Backs up, erases symbol, and keeps going. So as an example implementation, we have certain states. We have the accept state, which is represented by HA. So when we start out, we have three options. Our state is Q1, so we can either move to Q2, Q3, or to the accept halting state, depending upon what we are seeing with the head. If we see a 0, then we let it remain there on the tape and the head moves right and we move to the state Q2. If we encounter a 1, again same, we move to the right, it remains the same, and the state in this case is Q3. This keeps going till we are able to get to the accept state. I would suggest you take some examples and for each of these machines, develop a JFlap model and try them on a piece of paper to see how they work.